of the overlap is favorable. It will not move if, say, in the upper state, the region of maximum probability is far away from the region of maximum probability in the lower state. Because, why? That is the Frank quantum principle, which says that transition is always vertical. That means electrons change their configuration before the nuclei can change their configuration. So nuclei remain in the same distance and the electrons change to the upper state to the lower state. So the electronic change occurs without any change in the nuclear distance. Do you understand? Electronic changes occur without any change in the nuclear distance. They're instantaneous almost compared to the nuclear change. Right?
Yeah.
So there will be vertical transitions. So if there are no, if the probability is very low at this point for one of the states, then that state will not be reached. So this is the only restriction. But you cannot formulate it in a mathematical way. We have to look at each and every vibration state. So in general, theoretically, there is no restriction on vibration transition. Any vibration can theoretically occur. Any vibrational change can theoretically occur when it is accompanied by electronic change also. Right?
Yes, sir.
So let us now try to find out the energy difference when a molecule changes from the lower electronic state to a higher electronic state. The lower electronic state has quantum numbers, vibrational and rotational quantum numbers V double prime and J double prime, and the upper electronic state has vibration rotational quantum numbers V prime and J prime. So you know already the expressions for the rotation energies and the vibration energies. So you write them down for the upper electronic state and for the lower electronic state. Right? And there is a constant factor, mu 0, from Vi to Vk. So if we neglect all J transitions, then what will be the frequency? In this expression, for nu Ik bar, you neglect all J's.
Zero, sir. Mu 0.
Nu 0. Yes, nu 0. So, and what will be the other lines for different J's, for changing J's? We are keeping the vibrational change constant, V to V prime. Okay. Vibration change is constant. Within one, that makes one vibrational band. When the vibrational quantum number does not keeping vibrational quantum numbers the same, V prime and V double prime, then the rotational quantum number is allowed to change, and the rotational quantum numbers are given by the selection rules for rotational transitions. J prime equal to +1, -1, or 0. 0 comes only for sigma pi transition, and J prime equal to J double prime +1 or J prime equal to J double prime -1. You can write down the expressions for these energies for the upper state and for the lower state. So what is nu 0 here? What is nu 0 in this equation?
Sir, can you repeat what is the question?
Nu 0. What is the nu 0 in this equation? What is the physical meaning of nu 0?
Threshold frequency?
Sorry?
Threshold frequency?
No, threshold. No, it's not threshold. It is the frequency in absence of all J's. Look at that formulas. If we all put all J's equal to 0, then of course we get nu equal to nu 0, right?
Sir, why cannot with absent of J nu Ik 0? I mean nu naught can be 0?
No, nu naught cannot be 0. What I'm saying is nu Ik is equal to nu naught in absence of J.
Yeah, that's right. But is there any possibility that nu naught also can be 0?
No, because we are going from one electronic state to another. So electronic states are widely separated. And even if J does not occur, the electronic energies are very different. They are in ultraviolet region or visible region. So nu naught cannot be zero generally. Nu naught is the change in electronic energy in the absence of change in J. Well, Vi and Vk, they occur here. So Vi and Vk, Ni and Nk are the electronic indices. Vi and Vk are the vibration indices. So for a particular vibrational transition, in absence of rotational transitions, the line we get is nu zero, right?
Okay, now I understand.
Or you can say that if J double prime equal to 0 and J prime equal to 0, then we get nu Ik equal to nu 0. That will, of course, depends on Vi and Vk, right?
Yes,
Here
sir.
we take Vk to be the lower vibration number. I mean, vibration number of the lower electronic state, and Vi is the vibration number of the higher electronic state. But leave out all Ji, erase the Ji's, you get nu Ik bar equal to nu 0. That means nu 0 is the frequency of a hypothetical line which gives the transition from J prime equal to 0, J double prime equal to 0 to J prime equal to 0. If you put J double prime equal to 0 and J prime equal to 0, we get nu Ik equal to nu 0, right?
Yes, sir.
But of course, 0 to 0 transition is not allowed. 0 to 0 transition is not allowed. So in the central portion, there is a gap. Because what happens? If, let us say, if J prime is greater than J double prime, always, then these lines will give which branch? There are three branches. One for delta J 0, one for delta J plus 1, one for delta J minus 1. Delta J means J prime minus J double prime. J prime is the upper state J, and J double prime is the J in the lower electronic state. So J prime minus J double prime can be plus 1 or minus 1 or 0. If it is plus 1, if the upper electronic state is a higher rotational quantum number, it is J prime equal to plus J double prime plus 1, then we get a R branch. The lines we get are called R branch lines, R. If J prime is equal to J double prime minus 1, so the quantum number decreases, then we get lines which are called P branch lines. And if delta J equal to 0, we get Q branch lines. Of course, delta J equal to 0 can only occur for sigma pi transitions. So we'll get Q branch lines only for sigma to pi transitions. For sigma transitions, there will be no Q branch. There will be P branch and R branch. In R branches, the higher electronic state has higher J quantum number, higher by 1. And in the P states, the higher electronic state will have lower rotational quantum numbers, lower by 1. And Q branch will be present only for sigma pi transitions. But of course, 0, 0 is not allowed. So at the center, there will be a gap. Now, what I have done in the later portion is just calculated these things, these P branch and R branch frequencies, by taking J prime equal to plus minus 1, J prime equal to J double prime plus 1, and J double prime minus 1. If we take J prime equal to J double prime plus 1, we get the R branch. J prime is the higher one. And if J prime is equal to J double prime minus 1, we get the P branch lines, right?
Yes, sir.
So be careful about that, because in electronic transition, the vibration can change by any number. Vibration quantum number can change by any number. So V prime and V double prime are fixed. We are taking a particular V prime and a particular V double prime. We are concentrating our attention on that, on this particular vibrational transition. But this particular vibration transition will, for the description, its description will require many J's, because transitions can occur within the same vibration. There can be J equal to J double prime equal to, it can start from J double prime equal to 0, J double prime equal to 1, J double prime equal to 2, J double prime equal to 3, and from 0 it can go to J prime equal to 1. From J double prime equal to 0, from 1, J double prime equal to 1, it can go to J prime equal to 2 and J prime equal to 0. And if it is sigma pi transition, it can go to J prime equal to 1 also. So a particular vibrational transition with an accompanied by an electronic transition, that will have many lines, and these lines will form the band. There will be three distinct bands. One is R band, that is on the higher frequency side of the central line. The central line will always be missing because 0 to 0 transition is not allowed. So nu 0 is a hypothetical line. Nu 0 will not occur normally, but on both sides of nu 0 there will be many lines. One is called, on the higher side there will be R branch lines, and on the lower side there will be P branch lines, because in R branch the quantum number increases by +1, so the difference will be higher, and for P branch the quantum number J decreases by 1, so the P branches will be on the lower side, and at the center of the branches there will be a gap. Yes, any question?
No, sir, this question no.
Well, now the next question is, what is the structure of the bands? It's very easy to get the structure of the bands. You just deduct the energy of the lower electronic state, lower electronic vibration rotation state from the upper electronic vibration rotation state. We'll get different expressions for R branch, P branch, and Q branch. These expressions are given here. We check that out. Okay. This R, P, and Q.
Putting, as you said, putting delta J +1, delta J -1, and delta J 0.
If you put delta J +1, you'll get the R branch lines. If you put delta J equal to 0, you get the Q branch lines. If you put delta J equal to -1, you'll get the P branch lines. Right? P, Q, R. So P is the lowest, Q is the intermediate, and R is the higher one.
Yes, sir.
P, Q, R is just like the alphabetical sequence. Same sequence. P is the lower frequency lines. They will form a band. Q will also form a band if it is present at all. And if Q lines may not be present if it is sigma-sigma transition. And of course, the central line will always be absent because 0-0 transition is not allowed. So you can get the frequencies of the R lines and by the P lines. But one thing is there. You see that the rotational constant is different for the lower state and for the upper state. It's quite natural because the internuclear distance, equilibrium distance between the nuclei, they can be very different in the electronic ground state or electronic excited states. In general, they will be very different if the electronic state differs. So BV prime will not be equal to BV double prime. It can be greater than BV double prime, that is the rotational constant in the lower state, or the rotational constant in the higher state can be less than the rotational constant in the lower state. So both cases are possible. BV double prime, that is the rotational constant in the lower electronic state, greater than BV prime, rotational constant in the higher electronic state, or BV prime, the rotational constant in the higher state is greater than BV double prime, rotational constant in the lower state. Both are possible. And for both cases, you have to find out the frequencies of R, P, and Q lines. Okay?
Yes, sir.
Now, if you do this, you will see that for one case, can you go up a bit further? Yes, I ask you to do the calculations. Calculations are very simple. You take BV prime and J prime plus 1 minus BV double prime plus 1, and put J double prime equal to J prime minus 1, J double prime equal to J prime minus 1. What branch will that give you?
For -1, it is P branch.
J prime. Look, P branch is for change in quantum number by -1. So what this change in quantum number means? J prime minus J double prime, or J double prime minus J prime?
J prime minus J double prime.
J prime minus J double prime is -1. If that is true, then it will be P branch. And if J prime is J double prime plus 1, then it is R branch. Okay. So from this formula, we can find, you see I have written nu ik. Nu 0 I have explained is the central line frequency, which is missing. But the rotational components will be B V prime, J prime, V prime plus 1, and this, we have taken this vibration rotation into account. So, sorry, this will be J prime plus 1. No, we have not taken the vibration rotation interaction into account. We have taken the centrifugal distortion into account. So the rotational energies are B for the upper state, BV prime, J prime plus 1 minus DV prime, J prime square, J prime plus 1 whole square. This is the centrifugal correction. Have you read the centrifugal correction? I talked about it actually today. And B minus BV double prime, which is lower state rotational energy, BV double prime, J double prime plus 1 minus DV double prime, J double prime squared, and J double prime plus 1 whole square. Now, I think I've neglected this DV term. Let me see. When I took the difference, did we neglect the DV term? Go down.
Yes, sir.
The difference, yes, I think we neglected the DV term. The centrifugal distortion has been neglected. So we are speaking of pure, rigid rotators here. And if the rigid, we can take into account, if we take into account this rigid rotator properties, then we get the wave numbers for the R branch, Q branch, and P branch. Now, you see, these are the polynomials in J, right? Quadratic polynomials in J. Right.
So, what's the question?
These expressions for R, Q, and P lines, they are quadratic polynomials in J.
Right.
Take J, the initial, the lowest state quantum number. So this frequency as a function of J is a quadratic. So it can have a minimum and a maximum, right?
Yes, right.
So when will the minimum or maximum occur? It will depend on the difference BV prime minus BV double prime. If B prime is greater than B double prime, then let us see. Then there will be a maximum in one of the branches, and if B prime is less than B double prime, there will be maximum in the other branch. You can see this by differentiating. Differentiate this expression with respect to J. Take J as a continuous variable. Differentiate this expression with respect to J. Find the maximum. And you see only one of them, R or P, will have a maximum. Will have a stationary point, actually. If R has a stationary point, P will not. If P has a stationary point, R will not. Right?
Yes, sir.
So what happens near the stationary point? J changes, but the frequency does not change much. Right? That is the properties of stationary points.
Right.
So if that happens, that means in a very small interval of frequency, there will be many J lines. The J lines will be very close.
Yes.
Different J lines will be very close, and it will be so close that you may not be able to distinguish between them. They will form something like a continuum, and that continuum at one point will be that is called a band head. So the band head can be formed either in the R branch or in the P branch. It will not form in the Q branch. Normally it will not form in the Q branch, but it can form in the R branch or P branch. And you see the previous diagram. Look at the previous diagram, please. Yes, here you see the band head. In the first diagram, the band head is On which branch? Which branch? In the first diagram, which branch has the band head?
Sir, the Q branch. R branch.
R branch,
Sorry,
yes. R branch. So this is typical if B prime is less than B double prime. Then the R branch will have a band head. And after you pass the maximum, then the frequency of the R lines will start decreasing again. And opposite will happen in the P branch.
Yes,
If
P
B
branch.
prime is greater than B double prime, then the band head will be found in the P branch. And after the maximum is passed, then the P lines decrease with increasing J, but after the maximum is passed, P lines will start increasing again in frequency with increasing J. So at this, near the maximum or minimum, whatever you call it, the J lines will be very close together and they may not be resolved, and these are called band head formation. So band head formation can be either in the P branch or in the R branch. The band head will be in the R branch if B double prime is greater than B prime, and the band head will be in the P branch if B prime is greater than B double prime. You just go through this simple formulas and we'll see how they come. Just differentiate these new as functions of J. Neglect dV terms, and expand. See, BV is actually a quadratic in J because BV will be multiplied by J square plus J. So BV prime is J prime plus J prime square plus J prime, and BV double prime is J double prime square minus J double prime plus J double prime. So the thing is that BV prime and B double V prime will not generally be the same. They can be widely different, and this difference will depend. This difference will determine whether the band head is formed in the R branch or in the P branch. If the difference is very small, then there may be no band heads at all. But if the difference is substantial, there should be band heads, and the band head can be formed in R branch or P branch. And we plot this. See, what is the y-axis here? And what is the x-axis in these diagrams?
Y-axis is J and
Y-axis is J, correct?
Yes.
And x-axis is
Y-axis new
frequency.
Yes.
So we take J on the y-axis, and x-axis is the frequency, and we plot the lines, the frequency of different lines for different J's. In the P branch will be different from R branch. For in the P branch, the quantum number decreases by 1. So P branch on the lower frequency side. In R branch, quantum number increases by 1. So R branch will be on the higher frequency side. And in between, there will be a Q branch. And in the Q branch, there will be no such drastic changes. The line frequency will not change much.
Yes.
So the Q band, if it occurs at all, the Q branch of the total is called a vibrational band. P, Q, and R together. And there is 3 branches of the band: P branch, Q branch, R branch. The P branch may have a band head. That means many lines in a small vibrational frequency, in a small frequency region. Or R branch may have this head, but not both at the same time. Never. Q branch normally will not have a head, but many lines will be concentrated in a small interval. If a Q branch is present at all, Q branch will be present when sigma pi transition occurs. Otherwise not. And the central line will always be missing. The central lines means 0 to J0, J double prime 0 to J prime 0. This transition is not allowed for any change in vibrational quantum number. So this J prime equal to 0 to J double prime equal to 0 is missing, and the central line will always be missing. And you can find the difference between the first P line and the first Q line, first P line and the first R line from these formulas. That's very simple. You put the values of J in these formulas and try for yourselves. Now, the important thing is the explanation of the formation of band heads. Did you get that? How band heads are formed? Tell me, what are vibrational bands? What is a vibration band?
Sir, this band is completely straight line P and Q with respect to
What?
Sir, in first diagram, P and Q band is completely linear with respect to frequency, right?
No, it may not be. It is written, it is done like that, but it will bend.
Okay. In this case, some part is distorted, right?
Because you see, the functions are quadratic functions, so they'll not be completely linear.
Yes.
Q branch bends, P branch will also bend, but maybe less than Q branch. That might occur. And this bending is called minimum or maximum if the difference between B prime and B double prime are large.
Yes.
And this maximum minimum will happen in different branches. For the R branch, if the lower state rotational constant is larger than the upper state constant, and in the P branch, if the lower state rotational constant is smaller than the upper state constant. That you can very easily see from the formulas. Put the values yourself in the formulas and check. Right?
Yes, sir.
So, actually, this is a vast subject, and I have just touched it on the surface because there is no time for that, for more. So, what is important is the mechanism of the formation of band heads in electronic spectrum. Mechanism, how it is formed, where it is formed, in which branch it will be formed, and of course why it is formed. And what are the vibrational bands? What are the different branches? How does different branches occur? Why is the central line missing? Will the central line be missing always? When will Q branch be missing? When will Q branch occur? So these are the only questions I have focused on the studies of electronic spectrum. There are the vast things which we have not touched on, and we have not gone into polyatomic molecules. But something about polyatomic molecules you have to understand when you go to group theory. Have you read that? This group theory notes?
Sir, some part read, but not completely read.
Now tell me, you had a paper on group theory in the first semester, isn't it?
Yes, sir. Yeah.
So, are these familiar from that part? Some of this?
Yes, sir. Some part read group theory, and in this semester, sir, some extra part of group theory, sir, regarding particle physics.
No, as far as molecules are concerned, we are concerned only with these point symmetry groups. So, do you understand what point symmetry groups are?
No, sir.
No, sir, point symmetry groups are we missed them because that were in the second semester of solid state physics,
Yes.
but didn't cover that.
In solid state physics, you need translation groups, perhaps, isn't it?
It was point symmetry groups also.
Point symmetry groups also. Okay. In molecules, we need only point symmetry groups. Why are they called point symmetry groups? Can you tell me? What is the point about that?
Okay, so point symmetry group is every atom in the molecule we took it as point, and to where uh,
Equivalent.
seeing that whether it is symmetry or not.
Equivalent position.
Yeah.
You perform an operation on a molecule, and after the operation, each nucleus will be in this, not in the same position, but in an equivalent position, such as a equilateral triangle ABC here is turned, is rotated around the axis of rotation, and it becomes C. Well, it is turned clockwise, I think. So it will become CAB or something like that. So if C, A, and B are all the same atoms, then the second configuration will be equivalent to the first configuration. So this is symmetry operation. So all these possible symmetry operations on a molecule will form a group. You know the properties of groups when groups are formed.
Yes.
They have identity, and there's two elements will create another element and things like that. So you need not go into that. Know about the properties of groups. But why point? Why the word point is used? I think the answer is not clear.
See, we are doing some symmetry operations, and by doing so, at least one point, I mean, one atom.
1 point.
There is
No,
the atom
no,
is
no. It does not need one atom. 1 point at least of the molecule remains unchanged. At least 1 point. It may be more than 1 point. It may be a line. It may be a plane that remains unchanged, unmoved. All these operations form a symmetry operation. You see, the symmetry operations are given here. Rotation about an axis. So all the points on that axis remain the same. Inversion about the center. So the center remains the same. Deflection on the plane. So all the points in the plane remains the same. So all these are point group operations. And apart from these three, there is also improper rotation. That means you rotate the system about some axis and then deflect it in the plane perpendicular to this axis. This is called an improper rotation. That is also a point symmetry operation.
Orthogonal transformations with determinant negative.
Sorry?
These are basically orthogonal transformations with determinant negative. Yeah, the improper rotation.
Basically what?
Sir, orthogonal transformations with orthogonal matrix having determinant -1.
Yes, we are trying to understand it geometrically first. So geometrically, this you take the molecule, rotate it, or reflect it in the plane, or invert all the atoms about the center, and you get a new configuration of molecule. Well, next comes how can you mathematically represent it? Now see, all the molecules or most of the molecules are changed. They change their positions. So the change in positions, geometrical change in geometrical positions, if you can define a set of axes, you can specify all the atoms by their position in the coordinate axis, three-dimensional axis. And when you perform an operation, the coordinates will change. So it's changing from one set of coordinates to another set of coordinates. Rather, one set of coordinates for atom, they change to a different set of coordinates given a fixed axis. That is the effect of the symmetry operations. Now, how are this mathematically represented? How are these, operations? How are the changes, rotations or reflections or whatever? How are they mathematically represented? They can be mathematically represented by matrices, right?
Right.
If you fix the coordinate axis, you say this is the x-axis, this is y-axis, this is z-axis. Then the matrix for each atom is fixed by the operation. Each operation has a matrix associated with it, right?
Yes, yes. Right.
Now there may be many atoms in the molecule, 8, 9, 10. So each atom will have a matrix associated with it, and when you try to describe the whole change, this will lead to a very big matrix. So this will be a representation of the molecule of the symmetry operation, but not the only representation, because you can represent this molecule by a smaller matrix, even by one matrix, that is a single number. There are some rules of transformation of the matrices. These are called similarity transformations, and you read about that. Well, by the way, I don't think I can finish all the topics in group theory. Of course, group theory, I've just touched on the surface. So, can we meet another day for this discussion of group theory?
Yes, sir. Next,
Let's meet on
Thursday?
Thursday. Yeah, Thursday it would be cool. Let's meet on Thursday.
yes,
That's
sir.
all right. So, but before that, it will be of no use if you don't go through these notes. These are very easy things, because I have just made some definitions and basic theorems.
Yes, sir.
Nothing
Actually,
difficult.
figures are not clear. That's why.
Because that may happen if I draw. You go to the book, uh, because if I were taking a class, I could make the figures clear by moving my hands, by my gestures. That is not possible here,
Yeah, okay, I understand, sir.
because they are three-dimensional bodies. It is very difficult to draw three-dimensional bodies in two dimensions, and it may not be clear which operations we are talking about. For example, if there are three planes, three reflecting planes, which leave the system invariant, then we cannot draw the three planes at the same time and show how they're invariant. It's very, very difficult. And I'm not good at drawing, I'm afraid. So,
It's okay. We will read from this one. Just tell us. We'll see from it. The figures. Okay.
my favorite book is Cotton, Chemical Applications of Group Theory. You need not go, you just, it's a very elaborate book, and you need not go through all of this.
We follow the figures only. We will
Yes.
see from only your notes because there is no time for extracurricular
No,
reading.
what we'll do, you read only my notes.
Yes, sir.
And I'm telling you, the questions that will be put from group theory will be, we'll have to answer 5 small questions of 2 marks each, and 2 big questions of 5 marks each, right?
Sir, what is your weightage of 25 marks of molecular and laser
No,
physics?
I don't know, because I did not teach laser physics, and I don't know how they can bracket these two together, because the previous one was quite satisfactory. There's 20 marks in molecular physics and 10 marks for laser physics, and 20 marks for atomic physics. But now they're saying that there are 25 marks for atomic physics and 25 for molecular and laser physics. So I'm not clear how this 25 marks are to be divided between molecular and laser physics. I don't know. I've asked that, but I've not got any answer. But somehow,
I think your
laser
part
physics
will be,
isn't it?
sir, I think your parts will be 15 and laser will be 10.
But the question paper I made, that carries 20 numbers, 20 marks. It should be 10, like that.
Yeah, because if you like send like this, then we'll have problem in the exam. I think
Why?
because
It
laser
may be,
is so much covered. I don't
it may
think
be
it
more
is like
convenient to you, because in my course, in my papers, you have to say, you have to answer 20 marks from 40. But there will be more option. You will have to answer 15 marks from 40. Isn't it better?
so.
We have less time.
But
No, sir. The point is, total marks for your paper is not known, right? To you
That's right.
right now.
Yes.
So from 20, they will make it 15 if it is.
I don't know if they do it, then it will be advantageous to you.
Yeah. Obviously, if it is, the same question paper with more options, and we have to just
Yes.
answer only 15. Yeah, it is a very good advantage.
No, sir, but they can just reduce the marks and keep the number of questions same. So it will be then a lengthier one for us.
I mean, it's not lengthy.